Okay, do we need to turn that down just a little?
I know. Do I need to speak into a microphone or anything?
We've got a microphone over here, but that's the recording mic. Why don't you do a sound test in there?
Sound test is, can I be heard around, or is a microphone needed? Test.
We can hear you here on Zoom.
Okay, that's what we need then.
All righty.
All right, I believe that's it, so I'll let you go away with it.
Thank you.
All right.
Good afternoon. My name is Clayton Robertson. I'm from the University of Louisville. My research going on right now is ground and space-based dust observations of an overlapping galaxy pair named VV191. Specifically, I studied dust properties from dust attenuation and rending slopes that come from observations that come about whenever from the stellar populations of overlapping galaxies, specifically spiral galaxies, as we're going to see as the foreground galaxy of VV191. So the main motivation, about dust attenuation is that dust confuses, and it basically just confuses galaxy-wide galaxy population and distance measurements. And it's a problem throughout all astrophysics. And so what we want to do is learn more about it and study specifically attenuation law, which there are many different variations of it throughout. There's the Calzetti law, there's the Milky Way law, there's the different ones from the Large Magellanic Cloud and Small Magellanic Cloud, right? And right here is one specific motivation, an example of how dust attenuation will affect something that's been used. This is a big problem now, especially with the new James Webb Space Telescope, specifically with the Hubble law and standard candles. What happens a lot of times is from these different panels. So the top right panel explains that the more distant galaxies recede away faster. That's with the Hubble law, that's with redshift and distance further away. The farther away you are, the further galaxies are, the more they recede away faster. Well, standard candles, again, are type 1a supernovae. And so trying to be able to distance measurements of them will have an effect on specifically the cosmic microwave background for the Hubble law. So the chances of getting higher extinction, this is the top left one, it leads to standard candle distance underestimation. If AV estimations are correct in nominal galaxies, so especially, that is the bottom left corner, and the probability of encountering dust attenuation, specifically reddening, lowers with greater supernova host separation, leading to true distance overestimation. So depending on where this standard candle happens, it leads to an over or underestimation of standard candle distance measurements. This is a big problem for the Hubble tension, which is the difference in the Hubble, basically the Hubble constant between two different factors. One is the cosmic microwave background, and the other one is I'm blanking on it, but that's the I'm blanking on the other one. But that is the Hubble tension, is basically the derivation of the Hubble constant between two different factors. The one that this dust attenuation helps with is standard candles and cosmic microwave background. So that's one of the main motivations, and just one example of dust attenuation. So there's different ways to model dust attenuation law, and specifically what we do that is first proposed by Bill Keel in 1992 is using occulting galaxy pairs. That is two galaxies that are partially overlapping each other. Specifically, a spiral galaxy that is backlit partially by a smooth elliptical background galaxy, right? And so the configuration is here. We have a background galaxy. We hope the ideal schematic is a smooth elliptical galaxy, and the foreground galaxy is a spiral galaxy, kind of similar to our galaxy ourselves, the Milky Way. This configuration is ideal because what you can tell with the light lost from the overlapping region. So this depends on the symmetry of these galaxies. That is one of the main uncertainties, and that's one of the biggest uncertainties that come from this kind of measurement. And that's where we kind of study, and that's where the selection of the galaxies we use becomes very important. But the idea is you're measuring the light loss from the overlapping region, because this blue elliptical background galaxy is smooth and symmetrical. So we can see we need it to be partially overlapping, so we can tell how much light is lost compared to the background part that's not being overlapped. That way we can study the dust distribution of that foreground galaxy. Okay? We do this for different filters, and so what we have from, and I'll explain in a little bit, we have different filters that come from James Webb Space Telescope and the Hubble Space Telescope, specifically the 606 wide filter, the F090 filter from James Webb. We have different bands and different filters in which we can measure. We have different images of a specific galaxy, BB191, that I'll explain here in a second, that will determine kind of the dust attenuation along throughout different wavelengths. There's another way to measure dust attenuation, and that's through the Balmer decrement, and that should be, it's a little bit partially over the picture, and I apologize for that. But another way to measure it is through nebular gas emission lines, specifically the Balmer decrement, which is the H alpha emission line divided by the H beta emission line. And we have that through the George and Cynthia Mitchell telescope spectrograph of the McDonald Observatory in the University of Texas. That was taken in April 2022. Is that April? Spring 2022. Where you can measure attenuation, especially in the visible band, using this equation right here. And it's dependent on the Balmer decrement and the Calzetti, and these are called the total to selective attenuation slopes. And we usually, the most common values for KV, K of H alpha, and K H beta comes from Calzetti in 1994 and Calzetti in 2000. Those are the most commonly used selective to total attenuation slopes when taking dust attenuation measurements. So you can extract the H beta and H alpha lines coming from the spectrum that is given. This is IFU data coming again from the ground-based the ground-based spectrograph from the University of Texas. We can extract the Balmer decrement and put it in the calculation to measure out the attenuation itself. So we have two different ways to measure the dust attenuation of this foreground BB191 galaxy. And I'll explain a little bit more about this BB191 galaxy here in a second. But one is the occulting galaxy pair, which has its own method of measuring attenuation. That's right here, that uses the background and foreground regions that are not overlapped and the overlapping region to measure the attenuation. And we have nebular gas emission lines. Now, nebular gas emission lines are more sensitive to dusty H2 regions, and while this one is more sensitive to the stellar population and more specifically the stellar continuum, which is more dominated by a little bit older stars. So we have two different ways, and there's a discrepancy between these two that we can study. They're using these two different kinds of dust attenuation. Okay. Now back to VV191. VV191 is a beautiful galaxy. Picture's not the best because but we use different filters of F356, F090. These two are from 356, from James Webb Space Telescope. That's part of the PEARLS GTO guaranteed time observations from James Webb Space Telescope, and from StarsMog, PI Dr. Roberto over there. We have multiple different bands. The F606 and F336 come from Hubble Space Telescope. Ouch. And then the F356 and F090 comes from James Webb Space Telescope. What VV191 is a close galaxy where the foreground galaxy is about 230 megaparsecs, redshifts about 0.05, and it's a spiral SBC foreground galaxy that is partially backlit by a very nice, smooth, elliptical, symmetrical galaxy, VV191N. So it's a perfectly ideal schematic for what we're doing for measuring attenuation using occulting galaxy pairs. VV191 is selected. The observations were taken by James Webb, I think the summer after it launched, which is in 2022, July 2022. It's one of the first data releases from James Webb Space Telescope. It's a beautiful galaxy that's face on and hand selected because of its ideal symmetry that comes from it. And so this is what we did. So these are the two different ones. GCMS is from the spectrograph that uses H alpha and H beta. This is the map of the Balmer decrement with dust attenuation, and this is using the occulting galaxy. You can see the mismatch in the spatial resolution, and that is the main uncertainty that comes from these two measurements comparing each other. This, I can't see it, but I did have a beam on here that's not showing up here. But the idea is that the sampling for GCMS is around 1.4 kiloparsec sampling. Hubble is much, much better. That's about around 100 parsec scales. The mismatch in resolution is kind of an issue as far as direct comparison between each other. This is why we're actually, for cycle 32 on Hubble, which is due in like a week or so, I need to get back on that proposal. We want to find more, we want to get a few narrow bands that gets H alpha, H beta, and actually Paschen alpha that we can extract dust attenuation from emission lines at 100 parsec scales. But this is what we're looking at so far, and this is where we can map. This is over the same exact area between these two. The one at 1.4 kiloparsec sampling, and then just 100 parsec sampling. So in my paper, my first paper that compares these two, I need to get these resolutions to look like each other. I can't really do much with the spectrograph from ground base. It did an amazing job, but IFU data coming from the ground the sampling is not the best. So what you have to do is with this Hubble data is I can extract the region inside the overlapping region. And this is that green box right here. This is it zoomed in, is I can bend these and make these like super pixels. They're about 16 by 2/3 times 16 by 2/3 comparison with each other. And this is what I did over here. This is the map of the Balmer decrement from the spectrograph, the ground-based spectrograph. And this is the dust attenuation after I bend the super pixels coming from the HST telescope. And so we can have a direct comparison now between those two after the bend superpixels. And the error that comes from this comes from the deviation, standard deviation of the 16 by 2/3 and 16 by 2/3. So how that works is some are superpixels 16 by 16, some of them are 17 by 17. And it's a little bit of crafty coding that I had to figure out to try to figure out how to exactly bend the pixels. But some of them are 16 by 16, some of them are 17 by 17, and I can bend those together and I can match the resolution between those two. And that's where the comparison directly comes from. And this is kind of the results. Oh my goodness, some of the plots are not coming through nicely. Well, my paper is about to release soon and I can distribute that as well. That has the better versions of the plot here. But the idea is that I compare the attenuation from the occulting galaxy using different reddening slopes. And these different reddening slopes from the literature come from Calzetti in 2000, the Milky Way, small Magellanic Clouds, large Magellanic Clouds, Charlotte and Fall and Reddy in 2015, where they have derived their own reddening slopes. Some of them are galaxy-wide. I think Krekel in 2013, I'll show them a little bit, used IFU data as well. But these have different reddening slopes, along with what Bill Keel posted in 2023. His paper on VV191 has his own derived reddening slopes that I compare directly as well. And they should pop up here, but they are not. I don't know why, but they are in the paper. So read the paper. But these are direct comparisons. We see that they line up nicely with a little bit of scatter and derivation. This is with in that overlapping region that is in that little small box here. But the signal to noise cutoff of 2. Okay, so when you get to the outer skirts of this galaxy, it's a little bit harder to get signal noise, especially with the IFU data. So it reduced it from about 1,000 data points to only about 200. But we see that when it has enough threshold that the slopes follow what the literature says, even at scales of 1.4 kiloparsec. The error bars are in the paper too, so don't be alarmed. There's no error bars. I do have the error bars. Got to have the uncertainties. Okay. All right. Well, I don't know what's going on with the. Well, at least the slopes are here. Okay. So what I did is derived the attenuation from the H2 nebular regions using the equation that I explained earlier from the Balmer decrement versus the AV from stars that's using the occulting galaxy method. And we're seeing that discrepancies. So from the literature, these kinds of derivations of the dust attenuation that comes from the stellar continuum, aka like AV stars, comparing to AV nebular gas emission, they have a discrepancy of a factor of 2. But a problem with these kinds of measurements is a lot of times, due to the available photometry, that's about the entire galaxy itself, which mainly has kind of a bias that's towards the center of the galaxy, which are mainly dominated by young O stars and near the center, very dusty H2 regions. This is why a lot of times you see that big giant discrepancy between, it's about a factor of 2 of AV H2 over AV stars. What I found with IFU data going starting from the center and going to the outskirts, or starting close to the center and going to the outskirts, is that you see the discrepancy closer and closer towards the center, but as you get more to the outskirts, you see more agreement between these two attenuations. I don't know where the actual plots go, but at least the slopes are plotted here. That shows that R divided by RB, the protrusion radius is about 12 kiloparsecs for this galaxy. And around, when you get close to the protrusion radius of this galaxy, then you see more agreement between these two attenuations. So these kinds of discrepancies is what I want to go more in the smaller sampling of 100 parsec samplings, and because this is only for 1.4 kiloparsec sampling. We're seeing that closer to the center of a galaxy, it matches what the literature says at that kind of sampling, and we want to do that at even smaller scales. All right. So we studied this attenuation in an ideal overlapping galaxy pair VV191. It's a face-on spiral galaxy, partially backlit by an elliptical galaxy, mapping this attenuation. You measure from these different kind of filters. HST is F606 and 336, while James Webb has 090, 150, 356, and 444. It's awesome at 100 parsec scales, right? But to be able to compare to the IFU data from the ground, I have to basically bin them into superpixels that matches it to around 1.4, 1.5 kiloparsec scales. So these mismatch in scales are a big uncertainty from this measurements and from this paper, but I can match them, and I can, once I match them, I see it matches what happens in the literature when it gets closer to the center of the galaxy. Okay. In future work, I hope to map what's called a reddening slope, which is just AV divided by the color excess. The color excess is what's derived from the Balmer decrement as well. Throughout the entire overlapping region. So pixel by pixel we hope, or super pixel, which means that if we can't do a pixel by pixel, like a reddening value per pixel, because they might be too small, we might bin it to maybe 4x4, 6x6 kind of pixels for an encyclopedia reddening slopes from the center all the way up to the outskirts of the galaxy for dust attenuation. Okay. That's all I have. My name is Clayton Robertson. I will have any kind of questions now.
We're running a little ahead of schedule because of the first two that were out there. Have the first two speakers shown up online yet?
No. I mean, we got an email from Tom that he's not participating, but I have no information about Brian.
Okay, well in that case, I think we have time for questions for him.
Absolutely. Please, any questions?
And Dirk, if there are any online, then I'll let you.
I got a comment from Gary, said it was a very nice talk.
Oh, thanks. Thanks, Dr. Williger.
Yeah.
Any from in the room here?
Any questions?
And did you say that you're, one for me, did you say you're putting in a Hubble proposal?
Yes.
On this then?
Yes, it's due like what, in a week?
Yeah, about, yeah.
Yeah, cycle 32. We want to get in filters of, oh gosh, don't do this to me. It's 3 narrowband filters that's redshifted, and the redshift's about 0.0514. And it's, I think it's like the quad filter, 508 narrowband, the 680 narrowband, and then we want to patch an alpha one that's actually using James Webb, that's right. James Webb medium band filter, 140 medium band filter. And so we want to make one big proposal. Because they're narrow bands, that we just want these emission lines, and hopefully it won't be too much of it won't be asking for too much from the telescopes. We just want to extract these emission lines to where we can basically, where are you? This is the nicest one I could find. We can do this again, but at smaller scales. We can map it again, and then from there we can maybe map reddening values and encyclopedia reddening values where we see how they behave galactocentrically at small scales. But the scales is probably the biggest thing that pops out from these two comparisons from each other. And so to be able to match the scales at smaller scales, we gotta get better telescopes. Well, we gotta get the big telescopes.
So the big thing you're interested is how this changes over the galaxy, right?
Yes.
Wouldn't the IFUs be more useful for you?
See, that's what I was about to bring up. I was going to say, if my idea of using integral field spectrographs at low spectral resolution, but as a primary imaging camera, were adopted more broadly, you wouldn't have to worry which filters you choose. It would all be there.
You get everything there, but the only thing
And a range of directions.
Yeah, what resolution do you need? Because you have always something like 2-3 arcsecond resolution for the fibers, right?
Oh, well, I'll show you with mine for tomorrow then.
Okay.
Mine does not use fiber fed. It would be imaging resolution.
Oh,
It is imaging optimized.
That is awesome.
So there's a very good point that you brought up, but we are actually asking for Muse IFU data right now. Muse is probably one of the best. Yeah, Muse would be fantastic, and we are going for that data as well. We're trying to get as much data as we can to get for for, you know, like you said, and like I said, all galaxy-wide. So Muse, this one is, that GCMS did a great job on this. Space-based, a lot of times, one other thing that brings up is the 2175 angstrom bump. And the problem with, that I think that's one thing I do want to observe as well.
So that's this one right here.
Right here.
Yeah.
It's very blue. A lot of times you can't get, you know, obviously you can't observe from the ground because UV data doesn't really get through the atmosphere very well. So you're gonna have to ask for IFU data that comes from that as well. And so different kinds of telescopes are very, very, very useful for this. And so Muse telescope obviously is something that we are applying for. I think Keck.
Keck has the Keck Cosmic Web Imager,
Yes.
which is moderate spatial resolution, and but it's wide field, moderately wide field, but it's got excellent spectral resolution.
Yes. And so improving on IFU data, getting better IFU data such as Muse, and then better imaging such as Keck is something that we are working on. I don't know how many proposals we're working on right now.
Is Muse fairly narrow? Is Muse a fairly narrow field of view?
No, it's
I've
much
used-
bigger. So you said that KCWI is a much smaller field of view. This object doesn't fit on it,
Oh, really?
which is why I didn't go ask for it.
Okay.
We asked for Muse because it has a 1.5 times 1.5 arc minute view with 0.1 arc second sampling. So you get a spectrum every 0.1 arc seconds. And so depending if you switch on the AO or not, it will have similar spatial resolution as Hubble or better. And so if you're lucky, you get an IFU cube that has the same resolution as Hubble. Muse is oversubscribed more than James Webb.
I've used some of our archival data, and it's absolutely mind-blowingly fantastic. I mean, just using the DS9 viewer and scanning through the spectrum, we could see the rotation of the galaxy just because an emission line would roll across from one side to the other.
No, it's phenomenal data, but it takes a little bit, and it doesn't even take that long to do this. Like it take like half an hour maybe.
I think there was a chance that was able to almost get Muse data, and then it got rained out the day of.
Their collaborator got Muse data because if you go back to the 3D picture, because I'll tell you why, it had nothing to do with the science. So that the next one,
Which one? You mean the?
that one, yes.
Oh, sorry. Yes.
Right. So here's foreground galaxy, you see the background elliptical.
Foreground.
The reason that we got Muse time was because you see in the background elliptical, see a little arc there.
You see this little guy right here?
That was not something that we had seen before. It is a lensed galaxy. It's a passive lensed galaxy behind that elliptical. And so they got Muse time to follow up on that lens, and they're like, oh yes, and we're going to, this collaborators in the local yeah, we got Muse time, but Muse time doesn't guarantee time. You just get put in the queue. And make it through the queue, great.
There are multiple uses for this galaxy. I know collaborator Jessica Berkheimer studies globular clusters inside of the V191A background elliptical galaxy. And I know that Keel's paper in 2023 spends about half the paper talking about that beautiful Einstein ring. And so there are multiple different kinds of uses for this overlapping galaxy pair that is actually should work in our favor for future proposals and future work.
All right, any other questions? Well, that then, let's thank Mike. And coming up next is Tony Holberger himself. No, it's not. I'll be back.
No, it is Svarali Patil. scintillation arcs in nanograph.
What's on the new schedule?
Is this the old schedule?
Yes, that's what I told you. I told you that.
I thought you handed me the new one in the end.
No, that's only on this thing, on the memory stick. I gave it to you on the memory stick. I didn't have it printed. Okay, give me a second here.
They are online.
Sfaradi is on, okay.
So is this an online one?
You have, Sfaradi, you're giving the stock online, right?
Yes, that's right.
All right. So you should be able to share your screen.
Mhm.
Okay.
Okay, so let me see how to put this up on the board.
It's just, can you try to share your screen?
I think you need to.
If that's not possible, then we'll make you a co-host. Give me a second here.
I'm seeing a message that says I can't start screen share while other participant is sharing.
I will make you co-host. All right. Now you should be able to do it. Try again.
Unless we're still screen sharing this one.
Are you still screen sharing? Yeah, probably you do. Tom, Tim? Yes, now it works. Cool.
So are you able to see my screen?
I see your screen, I see your talk. Cool. All right, we're good to go.
Okay.
All right, see if I can make this any larger. Hang on.
Mhm.
Oh, shoot.
Yeah,
That was not it.
make it larger.
It was a suspiciously full screen. Here we go. All right.
Okay,
And Dirk, can you do the timing on this one here?
I can do the timing on this one, but don't worry too much about the timing. We have a little bit of time. This doesn't mean you talk for an hour, right? Okay, but it's all yours.
Okay, thank you so much. So good afternoon, everyone. My name is Swarali. I am a graduate student at West Virginia University and also a member of the Nanograph collaboration. And today I will be talking about scintillation arcs in nanograph pulsars. So let's start with introducing what are pulsars, right? And so pulsars are highly magnetized and rapidly rotating neutron stars. They are a product of the end of life of a massive star. A lot of them are present in supernova remnants. And the fact that they are remnants of massive stars implies that because stars are ubiquitously present in the universe, that means neutron stars or pulsars are also spread out everywhere equally in the universe, approximately. And that makes them excellent probes to study the interstellar medium. Another characteristic property of neutron stars is that they have highly stable rotation periods and they have impeccable timing qualities, which makes them an excellent tool for detecting gravitational waves. And over here is a diagram from the Handbook of Pulsar Astronomy that shows a typical structure of a neutron star. It has a rotation axis and a magnetic axis, and it gives out this radiation beam from its magnetic axis. And that's what we see from Earth as an observer. We see it sort of like a lighthouse effect of the radiation beam spanning across our line of sight. And so on the right is something equivalent to a Hertzsprung-Russell diagram for pulsars. And what we see here is the spin period of pulsars on x-axis and the spin period derivative on y-axis. And over here are typical young pulsars, which are sometimes present in supernova remnants. And as they spin down, which means as this rate of spin down increases, the pulsars basically go off the radar and we are not able to detect them anymore. And that makes them rotating radio transients, which sporadically sometimes emit radio waves. But some of these dead pulsars get recycled into binary systems. So when they come into contact with, when they come in the vicinity of another stellar body, they can eat up the mass. They sort of accrete the other mass from the other stellar body, and they get recycled into becoming binary systems, which are present over here. And we have so far detected about 3,000 pulsars, and around more than 250, 300 of them are present in binary systems. And the reason why binary systems are interesting, because most of the binary system pulsars are millisecond pulsars, which means their rotation periods are under
Okay.
30 milliseconds.
We cannot hear you right now, unfortunately. Okay, now oops.
Are you able to hear me?
Yeah.
Okay. Do you mind telling me which part was I muted from?
Oh, half a minute ago.
Okay, so I think that's just when I started explaining about binary systems. So when
Yeah.
when pulsars eventually slow down and they sort of die at the end of their lives, some of them, if they come in the vicinity of a secondary stellar body, they get recycled into becoming binary systems. They accrete mass basically from their main sequence companion, and they become into something called millisecond pulsars, which have a rotation period of less than 30 milliseconds. And these pulsars are interesting because they have even better they have even stable rotation periods, and the and rapid rotation period is really useful in using them as probes for timing arrays. And so that brings us to pulsar timing arrays, which are, as the name suggests, array of pulsars that we regularly monitor, and we regularly monitor and time them to detect gravitational waves at low frequencies that arise from supermassive black hole binaries, or sometimes even gravitational wave stochastic background, which is just a combination of all such massive events happening everywhere in the universe. And so the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, which I'm a part of, is one such pulsar timing array that, along with all the other international such PTAs, we collaboratively work and monitor pulsars in order to eventually detect gravitational waves. And for example, the image here is a picture description of what a pulsar timing array looks like. And we basically the idea here is that if a gravitational wave passes through this space-time, then we should be able to detect them as a correlated signal through all these monitored pulsars. And so there are a bunch of countries involved in this effort, and there is the International Pulsar Timing Array, which is a collaboration of all of them. The NanoGrav uses data from Green Bank Telescope, which I have used for this project. The CHIME telescope in Canada, VLA, and Arecibo, although it's not used anymore, we have historical data. And there is the Effelsberg telescope, Lowell, and a bunch of other from UK and the Europe. There is Meerkat in South Africa. There's UTI and GMRT in Indian Pulsar Timing Array. And the FAST telescope is used by the Chinese Pulsar Timing Array, and OSGRAV, which is the Australian Pulsar Timing Array. They use the Parkes telescope and the DSS and most. And so that brings us to the questions that drive my research. And those are that, can we successfully detect gravitational waves at nanohertz frequencies through the use of pulsar timing arrays? And what is the structure of the turbulent ISM, and what is the stellar evolutionary path of pulsar binary systems? And what scintillation studies is something that can bind all of these questions together and try and answer them to some capacity. So let's dive into the scintillation theory. It's basically a technical term for twinkling of stars. And when a radio signal from pulsar interferes due to the variations in electron density in the ionized interstellar medium, it takes different paths, and eventually it interferes and makes this interesting intensity fluctuation pattern. And a thin screen approximation is basically assuming. So along the line of sight, there might be a bunch of such electron density variations or turbulent parts of the ISM. So the thin screen approximation basically assumes that, and it's a good approximation, and that assumes that all of these features along the line of sight are basically situated as a screen at a distance from the Earth. And using this approximation, we can determine a bunch of things. For example, the dynamic spectrum, which we will look at in a second. But for this project, in order to observe these scintillation features, we use the Green Bank telescope that is situated in West Virginia, and it is a single dish telescope that can provide really high frequency resolution on source observations. And the high frequency and time resolution is a key for a project that involves studying scintillation. And so what we determine is, in order to see these fluctuations in the intensity of the pulsar, we look at something called the dynamic spectrum, which is for a subintegration I at frequency nu. The on-pulse and off-pulse spectra, it's an equation of the on-pulse and off-pulse spectra that we use to obtain the dynamic spectrum. And the secondary spectrum is basically a two-dimensional Fourier transform of the dynamic spectrum. And we see, for example, in this pulsar that is observed by nanograph, we found scintillation arcs. So on the left is a dynamic spectrum, and we see these intensity fluctuation patterns over here. On the x-axis, there is observation time, and on the y-axis, there is frequency. And on the right is the dynamic spectrum, where we actually see the scintillation arcs. And these are sort of parabolic features. They're known to be parabolic, but there have been theories that they could have other shapes too. And there is another pulsar that we saw a scintillation arc for. So we observed 6 pulsars with the Green Bank telescope. We are scheduled to observe a few more, and we found scintillation arcs in 2 of these. And so the presence of a scintillation arc basically means a presence of a thin screen along the line of sight between us and the pulsar. So that implies that there is some sort of turbulent structure along the line of sight, and we could follow up that as in a multi-frequency analysis. And also these sort of delays that scintillation introduces are really useful because they should be accounted for when we are timing pulsars. And so this parabolic arc curvature given by eta. So basically the Doppler time delay on y-axis is an equation of the arc curvature. It's a parabolic equation of the arc curvature and Doppler frequency. And so for a screen at distance ds and a pulsar at distance d, we can find out the effective velocity of pulsar, and therefore determine, just from observations of eta, we can effectively determine the pulsar distances, which are crucial in pulsar timing, and also pulsar velocities. And so in summary, while scattering or scintillation is a nuisance in pulsar timing activities, it is important in order to improve sensitivity of our PTAs. It is important to account for scintillation. And so individual scintillation studies, dedicated studies of pulsars are important. They can also tell us a lot about the interstellar medium along the line of sight. And studying arc curvature variations over long term are useful in determining orbital parameters, pulsar distances, and also velocity estimates, which are crucial for PTAs. Yeah, that's my talk. Thank you so much for your attention. If you have any questions, feel free to post those in the chat.
Don't forget to unmute the mic on the host computer.
here. All right, I'm unmuting the one in here. Go ahead.
So you mentioned the scintillation arcs on the pulsars coming from like, a approximate thin screen of interstellar medium. Do we see a similar effect of that arc as it passes through our own atmosphere? How would we separate those out?
Were you able to hear that?
No, can you repeat that?
Yeah,
Come up
maybe.
here. I don't want to move this or we might lose the connection again.
Where's the sound coming from?
There's the microphone.
Okay. I was just curious, so you mentioned the scintillation arcs coming from like the pulsar light passing through the interstellar medium. Do we see a similar scintillation effect as it passes through our atmosphere, or how would we separate out those two different effects?
Yeah, I don't. So I think atmospheric scintillation effects do not occur in radio regime. So we do see, so when stars twinkle, we do see those in optical regime by our eyes. That is because of the atmosphere. But I don't think in radio regime, the atmospheric contribution does not occur. Because otherwise we would be observing them from space-based telescopes. So that's the beauty of observing from ground-based telescopes, is that in radio regime, those effects are really small.
Thank you from Kyle there. Other questions in person? All right. Any online there?
I don't see anything online.
Okay, well, that's nice to see then. And of course, with that, the recent, last year's announcement from Green Bank about the, what was it, the stochastic background that they had announced seeing there, then that's nice to have some new results coming out of the pulsar timing, the nanograph project. All right, well, let's thank our speaker again then.
Thank you so much.
Okay, on the news schedule then, since I don't have that one printed up then, what are we up to now, Dirk?
On the news schedule, we are up, I think it's like we do poster announcements, which means you will tell us why people should look at your poster.
Okay.
It's your elevator speech. Okay, go in front, there's the microphone, and advertise your poster. Why do you want people to come to your poster?
And make sure you introduce yourself first.
Yes. Where you're from, who you are, and why is the poster interesting?
Hi, everybody. My name is Tristan Stanek. I'm from NKU. I'm a freshman. And you can introduce yourself.
My name is Mario Mata. I'm from NKU. I'm also a freshman.
Our poster is about detecting AGN, active galactic nuclei, in extreme flux states with SWIFT. The poster is pretty cool. We get to look at a whole bunch of different light curves and how we research different AGN to see the variance, the p variance, and basically just using SWIFT to examine the different, examine our hypothesis, which is that smaller black holes will have, smaller black holes are black holes with higher accretion rates will have a higher variability.
And did you see that? Did you see that the smaller black holes have a higher?
Okay, yeah. So with the study, as of now, we don't see a correlation with any AGM properties and higher variance, but we have a very small sample size. So hopefully with a higher sample size, and we can look at more AGM properties, we'll see something that correlates with the variance.
Thank you. There's another poster. Go for it.
Hi, I'm SM Rafiathan, a graduate student at University of Louisville. And my poster is about exploring the mass metallicity relation in open clusters inside the Milky Way galaxy. So here what we do is we use Gaia data release tree, DR3, to figure out, first of all, the member selection of the open clusters through clustering algorithm called HDB scan. And when we separate out the members, we analyze the individual metallicity of each stars, and as we try to see the metallicity relation in an open cluster, how is it related. So yeah, we saw a negative power law relation in the open clusters, most of them, and some of them are there is a discrepancy, there are outliers. So yeah, so that's it. Thanks.
Thank you. So now we take a coffee break until 1500 p.m. And so we will also be online back at 3 or 1500, which is 1900 UT.
3 o'clock?
Yeah. That's on my schedule. All right, I will stop the recording too for now. And stop recording.